Let me start by thanking everyone who joined today. I know that these are difficult times across the globe in many parts of the world, many countries. We have lockdowns and all sort of issues, having to stay home and take care of families. So I know it's complicated. So I appreciate everyone taking time to join the talk. Hopefully, this will be some time to think about something else, maybe learn something new. The talk today will be about Pravega, and in particular, we will be covering some of the key features of Pravega, critical features that we believe are important for stream processing, and interestingly, how they connect to each other or even interfere with each other in certain ways. So Pravega is storage for data streams. The idea of Pravega is that we want to expose storage. We need to expose a stream as a core primitive for storage. And when we talk about streams in Pravega, one of the core concepts that we have is the one of segments. And the reason why segments are important in Pravega is because they enable us to do some pretty cool features by composing them into streams. And specifically, some of the things that we can do with those segments are scaling transactions, even state replication, and storing internal data for watermarking. Those are some of the critical features that we have developed with Pravega, and that we were able to do because of this flexible concept of segments that we expose internally, and enable us to compose in this way. So Pravega is an open source project. It's we have a website, pravega.io, which I encourage everyone to go check and look at the documentation, learn some more about how to run it, about the internals, and even if you're interested in contributing to the project and working with us. So that's a pretty quick summary of what Pravega is. The remainder of the talk will be about going into details of some of these things, and again, in particular, about the core concepts, the critical features, and how they relate to each other. Let me start by giving the landscape as we see it between Pravega and Apache Flink. So we have on the left-hand side, we have various data sources, and in particular, data sources that are continuously producing data, which we are calling data streams. So for those data streams, we want to ingest them, and we want to process them in various ways. The processing doesn't need to be as simple as one single stage. We can compose stages and even interleave stages of storage and stream processing, forming directed graphs. And there are various reasons why one would want to do that. You have data from, again, a large number of sources. You might want to visualize the data in certain ways. You might want to raise alerts from, say, a fleet of servers. You might want to have like near real-time insights from the data source of their application, recommendations, actionable insights. When you go to a customer, you want to know some data that could be useful in that conversation. So those are all possibilities for output out of processing this all this data coming from these data sources. So that's the landscape, and that's the foundation for what we're going to discuss today. How Pravega is that storage system for streams, and how Apache Flink is that stream processor, and the combination of them, how they work together, and how applications can benefit from this combination. Let me talk a bit more about data streams so that we are on the same page about what it is that I'm saying. So data streams, at a high level, they are streams of data from distinct data sources. They can be end users. You can have online applications, social networks, online shopping, where end users are continuously streaming events. Could be status updates in a social network. Could be, again, transactions or search in an online shopping application. But it's not only about end users. It's also about machines. And machines could be a fleet of servers that you're monitoring. They are continuously emitting telemetry. It could be computer systems, so tools and services that are continuously also emitting, I don't know, say logs. So if you think of Jira, Git, Jenkins, all these things are continuously emitting reports, events that you might want to capture. There's also IoT and Edge, which are buzzwords and hot topics these days. But the reality is that there are many of these devices, these machines out there that are producing data continuously, and that will continue to produce data. Future applications that will come and have even more of these sources. So those are examples of applications which match this model of data streams that we are talking about. A couple of applications that we have seen in our exploration of the user space and talking to customers about Pravega and Flink are, for example, drones that are streaming video plus telemetry, where the idea is that we want to ingest that video data, that telemetry data, and process it. You might be interested in also reprocessing it at some later point in time. And so it's not only ingesting and processing it once, it's also the ability of keeping it and reprocessing later on if that's needed. And concrete applications we have seen that we're doing it were in the agricultural space. Companies interested in looking at the health of cattle. Another one is for airplanes, maintenance of airplanes when they are parked in an airport between flights, look for structural damage. So that's those are concrete applications where we have seen where we have applied these concepts. Another one is the one of industrial IoT, where you have a factory floor and you have streams coming from, say, video, or you have an even more telemetry, but just signals that help you identify if there are problems in your production chain, in the parts that you're producing, all of that. And there is one document that I'm sharing in the slide. I don't know if you're going to be quick enough to type that, but it's a long URL. But it gives a description of a use case in which which Pravega has been successfully used for industrial IoT. Now, stepping back and thinking about properties of these data streams, one natural way of thinking about these data streams as one single sequence of events. As new events, messages, records are being produced, I'm just appending them to what I'm calling a stream. But it's not that simple, because a lot of the cases that I have mentioned, it's not one single data source, it's not one single end user, it's not one single sensor. It could be many of those. And so in reality, you have a continuous flow of parallel streams, if you will. And so it looks more like what we have in this slide right now. So this parallel flows of events, record messages that are coming in and that we need to ingest. But it doesn't stop there, because many of those workloads are not static. So I cannot consider that it's the volume of data or the byte rate even is always the same. There could be spikes, there could be times in which it drops. So you can think of periodic cycles, I don't know, daily cycles, weekly cycles, that could induce fluctuations like this in the workload, or even some unanticipated events in which you have every once in a while a spike that you need to deal with. And so that's another aspect that needs to be taken into account when you're thinking about streams and when you want to ingest and process it. Another one is that streams they are unbounded. You can start a stream, start producing data, and that can keep going for a long time. It can keep going for weeks, months, maybe even years. And traditionally, systems have split that data between older historical data that is perhaps stored in one system and the fresh data it's stored in a messaging system. I'm going to call this the lambda way, referring to the lambda architecture. But ideally, the abstraction should be in such a way that you don't have to reason about your streaming that way, splitting it between old and new or old and fresh, and just look at a stream as one single abstraction. Now, all those properties are about the ingestion, the write path. But the read path is also very important because the ingestion is just the first stage in acquiring the data. Now, the next steps will be processing the data, deriving even more data out of it. So that's connection with the pipeline downstream is also very important. So read scalability is another very critical part of dealing with data streams. So that's the key reason why we endeavored into reasoning and building a system which has a stream as a core storage primitive. So you're able to stream in and stream out. So that's why you see when you're writing your data, and that's why you see when you're reading your data. We have done it in a way that it captures properties that we believe are important if we're talking about cloud native applications. So the amount of data that it's able to ingest is unbounded. It must be able to accommodate to workload changes, so it must be elastic. It needs to be consistent, and it needs to be able to tail and deal with historical data out of the same abstraction without having to split a system into different storage dependencies. Now, the recipe for this is Pravega, which encompasses a number of critical features that we believe are necessary for building these pipelines. And they are exactly once processing, so don't miss, don't duplicate. Checkpoints are critical for Flink, and having checkpoint in Pravega connects the read side of Pravega to the Flink checkpointing mechanism. Durability, so the ability of replaying, so going back to a position of stream and replaying, so that the data needs to be there. If that needs to happen, so that reprocessing needs to happen. Scaling, dealing with the workload changes that I mentioned, and watermarking, advancing events, ingestion, processing time in a way that is correct from the perspective of the application. So now I'm going to pass the token to my colleague Tom, who is going to go into more detail on the interrelation or the connection between all these features. So Tom.
Thank you, Flavio. So if you look back at that list, almost all these requirements are sort of essential not just for Pravega, but for any connector that's going to offer streaming data into Flink. And if you were to try and graph a dependency graph of how these things affect one another, or how designing to solve problems for one of these will impact the other, you'd end up with this. As you can see, everything's interlinked with everything else, because these concepts, well, they sound nice and orthogonal. They really aren't. They really interplay in complicated ways with one another. And so I'm going to sort of give an overview of what that kind of looks like. So to start out with, Flavio talked about IoTs and doing social networks or server metrics, et cetera, et cetera. You can do all those sorts of use cases on Flink, but almost the core thing that you're probably going to end up doing is doing some sort of window-based aggregation, right? And this is built into Flink, and virtually every application ends up doing some form of this, right? But for this to work, you need a very important feature, which is you need to have the writer supplying actual time information so that you have event time that's anchoring these events, such that you can assemble them into windows with respect to those time windows. But it's not just enough for the writers to supply the time. You actually need to have what's called a watermark. And this is another notion built into Flink, which is a very specific contract, the definition of which is going to become very important later, which is that when you reach your watermark, you're saying all the events below a certain time have been received, and there may be some allowance for events to come in late that have a timestamp below that, but that usually is expensive and involves some sort of compensation logic, or in many applications just may be thrown away because they're irrelevant or something. So it's definitely undesirable to have late events, and certainly you don't want any sort of connector that's connecting into Flink to be causing that. Or at least not making it worse. So so sticking within that contract for a connector is very important, and it's not so trivial to do. It ends up impacting a lot of different things. The first requirement that it imposes is that you actually have order. And you can imagine in this example, right, where if you say, watermark 6 has passed, we have all the events below 6, and those events 6 and 7 end up getting transposed, it's going to make the situation it's going to cause event 6 to be late and cause some complication logic on the application that's not permissible. So immediately you need to have order guarantees out of the gate. But what's more, that's not just a local order. That's actually a global order, because if you think about it, they have many event processors, each of which are emitting events in parallel, and they may have different notions of time. Not inherently because people disagree on what time it is, but because one event source may have some amount of lag. In particular, if you think about things coming from a cell phone, right? Like it may be some delay before it gets into your network and ends up being processed. And different devices may have different amounts of delay. So to be sure that there isn't any more data coming in, you need to have some sort of global view of time, which it's not just a matter of having time, but you need to coordinate that time with specific positions in the stream. So this is going to dictate, so to produce a watermark, you're not only relying on order, but you're relying on even stronger assertions about what's going on in the stream and being able to refer to specific positions in it. And this actually impacts the way that exactly once works, because you need to have position tracking in both cases, right? So if you imagine you have this event source and it's writing some data to a stream, right? It sends 3 events and then ends up getting a disconnect. In order to not have duplication, it's going to need to resolve whether or not it has sent particular events before sending more. So that can either be in the form of deduplication on the server side. We're detecting, oh yes, we've advanced beyond this position and everything before that is in fact durably stored. Or it can be in the form of the client asking the server, hey, how far did I get? And then it's sending back a position object saying, hey, you've got this far. And then it can resume from there. So this notion of position tracking actually applies for both exactly once and ends up being a requirement for watermarking. And this actually is deeper than that, because you need to think about how accurate you can make time windows. In order to be precise, you not only need exactly once for delivery, because you're going to have events coming in later, you can have crashes, right? So if you have 3 windows and one was closed and two are open, and then you crash in the middle of the processing application, in the middle of the processing, it's going to need to restore from some point and reconstruct its state in a way that's not going to duplicate messages, right? So this is very much tied into how exactly once works. And the way that Flink solves this is via restoring from a particular point. But if you think about that, that interacts very strongly with watermarks, because the guarantee about watermarks is that you've received all the events prior to a particular time, and presumably you've decided to process those. So if you are suddenly backing up, that can end up being, if it were naively implemented, which it isn't, could end up being a violation of that contract. And so you have to have the watermarking logic tied into the fault recovery logic, which it is. So the way that Flink does this is it expects each connector on the source and the sink side to track where they are and to be able to resume upon recovery from a particular point. And that notion is called checkpoints. So every so often it records the state to a particular position and then says, okay, we're going to be able to restore the in-memory state to this position, and we expect all the inputs to be able to rewind to that particular position, which is actually a fairly strong requirement on any sort of delivery system to be able to say, okay, we want to be able to back up and get the exact same thing that we just got. And that has implications for architectures as well. So you end up having to persist the state internal to the application, which is fairly straightforward generally, because if you're using Flink's in-memory persistence, it handles all of that for you. But it also has implications for the durability on the send side, because it's going to need to be able to give you the same. It's going to need to provide consistency, and it also complicates the sinks much more than the sources, because if you think about it from the perspective of the sink, Flink is outputting some data, it's producing data as it goes along, and then all of a sudden it says, okay, wait, we're rolling back to a checkpoint, which means that data that was sent now needs to be not sent, or deduped at the very least when the data is resent. But that dedupe may not be quite identical depending upon the application. It might have, processing time embedded into it, for example. So it's not completely trivial to perform. This also means that the contract of watermarking is influenced, because if you remember, when a watermark goes through a sink, you're saying that all events prior to a particular time have been received. But if a checkpoint ends up causing you to back up and say, oh no, now we're going to resend from prior time interval, we actually can only advance time at checkpoint intervals. So it's actually a subtle interaction there between these two systems. And of course, none of this takes into account scaling, right? If you imagine you have multiple workers in parallel processing different portions of the key space of different events, right? And you can add, if load increases, you may end up subdividing that and adding a new worker. Or, for example, one worker could end up, in this case, the blue worker ends up falling behind because it's processing more data than the others, and so some of that data ends up getting handed off. Well, that's going to impact virtually everything I've already told you. It's going to have implications on how do you do exactly one's processing, because you're going to have things that are being handed off from one worker to another, which has implications on ordering guarantees. And of course, watermarks are dependent upon that, because now the green worker is suddenly receiving data that was coming from the blue worker before. So it can't perform a watermark based upon locally available information. You need a global view to have time consistent. And it's also going to impact redelivery guarantees, because when you're talking about potentially having the number of workers change, if you have a failure and recover, you're no longer seeing the same events from the same workers. So it complicates things on both the send and the sink side. In short, dealing with all of that together at the same time ends up being very complicated. So much so that I can't really describe sort of the architecture of just what everything looks like in purely abstract terms, because if you change one thing about the way that scaling works, you have to re-architect how checkpoints and watermarking and everything else is done. So instead, what I'm going to do is hand it back off to Flavio, who's going to talk specifically about how Pravega deals with all of these issues.
All right, thank you, Tom. So I will cover a bit more detailed the aspects of our implementation, our design implementation of watermarks, and then I'll connect that to Flink. To talk about watermarks, let me illustrate by showing a stream, how a stream in Pravega should look like. So stream Pravega, as I mentioned right in the beginning of the presentation, is a collection of segments, and those segments can be placed in parallel, or they could be placed sequentially. And so I can, like I have in this stream in this slide, I can start from, say, one segment and split into 2, then into 3, then into 4, then back into 3. So this kind of dynamics of a stream is something that we expect for an application, for a stream that is being used by a real application. Because of that, we need some notion of a position in the stream, and we call that a StreamCut, which is, you can think of that as a vertical cut of segments of a stream. You're spanning a set of segments, and that gives you a collection of offsets for the segments, and its collection gives you a position in the stream. So the StreamCut is a position in a stream. Now let's see how that's useful for watermarking. So for watermarking, what we do is we have the event writers appending events to a stream. So there are these 6 events that have been written to a stream. At some point, the writers will indicate to Pravega that they have advanced time to a given time t, and that corresponds to their own observation of what the time is. And so they go and notify Pravega via an API call, nodes time, saying what the time is. So internally, Pravega will collect that data and will periodically generate what we call a watermark. So a watermark for us is a triple that contains a lower time bound and an upper time bound. The lower time bound is the minimum time data from the recent collection of time that the writers have informed, and the upper will be the maximum of that collection. And the StreamCut is a position in the stream. So that position in the stream should be such that all the events indicated, all events that have a timestamp that is lower than the one indicated by the lower bound are for sure before that position. So that's the guarantee that the watermark object gives us. Now, using that, on the reader side, we have the readers will read the events from the segments, and when they have reached a position that matches their watermark, then they can update the time information or the low watermark that they will expose to the application via the API. So this will become a bit more clear when I talk about Flink. So let's go into that. Let's talk about the conjunction of Pravega and Flink and see how all this works. We have implemented connectors so that a Flink job can work with Pravega. So we have a source connector and a sync connector. So the connectors are open source. I'm showing the URL of the repository down in the slide. And when a Flink job is using a Pravega stream as a source, what we will have is each source task will run a Pravega reader, and the collection of the Pravega readers across source tasks will form a reader group. And that reader group will be responsible internally for doing all the assignments of segments and rebalances that are needed. So all the complexity of dealing with the dynamics of segments changing due to scale, for example, that is all hidden from the application, in this case from the Flink job. Now for watermarks, what we do is we expose an API that enables the application. In this case, it will be the Flink connector to get the current time window. So the time window has 2 attributes, a lower bound and an upper bound. So the lower bound will be the minimum time before the current position of the stream, given by a mark, by a watermark from the ones that we have generated when writing and when noting time. So that minimum time will give the lower bound of the time window, and the maximum will be the next mark after the current position of the stream. So if you think of the position of the reader group as a cut, I'm comparing the cuts of that is this position to the marks that I have generated from the time information that the writers are giving. And so we use that to generate watermarks for a Flink job. In the connector, we implemented a lower bound assigner. So that lower bound assigner extracts a watermark by taking the lower time bounds from the time window. So it periodically requests the time window and takes the lower bound and makes it the watermark. And to use that in a Flink job, we make a call to with timestamp assigner, adding the lower bound assigner, and implementing a method to extract the timestamp. So you still need to extract the timestamp. In this case, I'm assuming that the samples I'm processing have a field that is a timestamp, and so you just return that. But I'll talk a bit more about the operation of the connector. So that is one aspect, how to get the timestamps and the water and emit the watermarks. Now let me talk a bit about the checkpoints, which is something that Tom has covered. When Flink needs to start a checkpoint, the way we'll do with Pravega is it will initiate a checkpoint in Pravega. So you make a call through the reader group API to request a checkpoint. So that will trigger an execution internally that will be coordinated by the reader group. So the reader group, they will talk to each other and share state about where they are, and that will be used to determine the checkpoint, the position that comes in the checkpoint. And as part of that coordination, each one of the readers will emit a checkpoint event. So that checkpoint event essentially bootstraps the execution of the Flink checkpoints. The emission of marks that are going to flow through the graph, that starts with those checkpoint events. And finally, when that's processed, the checkpoint master receives the checkpoint, which it keeps as part of the checkpoint state, and that's needed in the case you want to roll back. If you want to roll back, you got to be able to tell Pravega to rewind to that particular position given by the checkpoint. In our connectors, we also enable exactly once end-to-end by using transactions. So we do enable transaction rights. That's one of the questions that was asked in the Q&A. And the way this goes is, as I was saying, it starts with a checkpoint, and then the marks flow through the graphs. When they reach the sync tasks, then it's acknowledged to the Flink master, and that's when the Flink master receives from everyone. Then it tells the sync task to commit the transactions, and then that's done. Right? So that's the point in which the data becomes visible on the output Pravega stream, and that's the two-phase commit protocol that's implemented as part of the Flink checkpointing mechanism, and that we combine with this Pravega checkpointing that is needed so that the source also satisfies the required properties. What I want to do now is give a little demo of watermarking, but I have to hope that this screen sharing is going to work. I haven't tried this application, so let's see if this is going to work okay. Okay. So here, actually, before I do that, okay, slides, good. Let me talk a bit about the setup. So in what I'm going to do is I have a set of input files. These are very simple files. They have the sample events, which are which comprise an ID, counter, and a timestamp. Then I'm going to ingest those files through transactions to a Pravega stream. Then I'm going to use a simple Flink job to process the events in that stream. So I'm windowing the samples, and I'm setting it to be in windows of 1 millisecond, but in reality, I'm cheating it a little bit because time here is given by the file IDs. So the time unit here is a file ID. So 0 corresponds to file 0, 1 corresponds to file 1, and this is all to make it simpler to understand and reason about the output. Okay, so this is what we are about to see. So let me go back to sharing. Okay, so here's what we have. No, not this. I want to show the files. So I have all these files. I have 50 files. I have 50 files total. And then what I'm going to do is I'm going to start Pravega standalone. Okay, so Pravega is starting. And then what I'm going to do next is start the writer. So the writer is going to read from those files and we'll start adding those to the stream in a transactional manner. This is going super slow.
Hey, Flavio, increase
Okay,
your
now,
font size.
all right, then I hopefully this is better. So what I will do, I'll start Flink. Not here. Okay, so I can see the application is writing. I have started Flink. Now, what I need to do is I need to start the simple job that I have. Okay, now let's see that on the Flink dashboard. Okay, so job is running. Now, we want to see metrics. We want to see the input watermark. And what we expect to see is this input watermark going up over time. Now, for each one, okay, so it has finished ingesting. So for each one of these transactions, what we do is we note time only at commit time. So we don't note time periodically or in between messages. We do at the time that we commit. In fact, the commit call has time as a parameter, and that's what we're doing for each one of these files. We ingest the whole file as a transaction, and then pass the time, which is the file number in this particular case. Yeah, I don't know if this is going slow. So let's see. Let's look at the All right, so it has finished. So this is the output file. So it has produced all the windows up to 49. So from 0 to 49. But the dashboard for some reason is not. Oh yeah, okay. So I updated once. This is going to be slow. So the watermark has reached the point of 49, which is what we expect. The last file is 49, and that corresponds to the last time. Okay, so that's what I wanted to show. Let me go back to the slides. I'm ready to wrap up. So everything is connected. We talked about relevant features for stream processing, exactly one semantics, checkpointing, durability, scaling, watermarking, and the fact that if you're trying to put all them together in a system, they influence the design of these mechanisms. They influence each other in fundamental ways. So they are all connected. We have discussed the implementation of this of these features in one particular system, which is Pravega. So recall that Pravega is a stream store, and it's open source, supports all the above features. We have also covered how Pravega and Flink connect. We have a source and a sink connected that you can use with your Flink job, and it enables your job to do both, ingest data from Pravega and output data to Pravega. So with that, let me conclude the presentation, and I don't know if we have time for a few questions, but otherwise you have some interesting pointers in this slide.